sorry. Yes. La régie, vous pouvez juste afficher. Yeah, no, it is good. So there will be. La régie? Allô? Attends, je vais faire. C'est actif peut-être, non? Oui, mais si vous m'entendez, la régie, vous pouvez essayer d'afficher juste l'écran pour voir si genre. Ça marche?
Redis-moi, tu m'as dit quoi? Redis-moi, j'ai pas entendu ce que tu m'as dit.
Côté régie, vous voyez le PC ou pas?
Et je vois ça. Ouais.
C'est bon. Ok. Perfect. Ok. Merci.
Il n'y a pas de souci.
Just plug it in, right?
Yeah, perfect. Thank you. Do you know when you?
Maybe I should leave it here. So
You can,
As you like.
if you hide it behind.
Yeah, it's better to just leave it here.
Ok, perfect. Hop.
You just have to.
So I sent my PDF via email.
So, which talk is first? Is it the rate preserving reductions for Blackwell approachability,
It's
or is it different?
no,
Do
it's
you know?
online learning.
Online learning and scheduling with delays.
Yeah, the first. Ah no, the first one of online learning.
Okay, but I don't have to keep track of that, right? I'll just see it and then I'll announce.
Yeah.
I'm Sharon. Yeah.
Excellent. Can I call the people to come in?
Oh, sure.
Yeah.
I think.
Fichez-le.
Speakers are here.
The first what is it?
Yeah, no. So I thought the first talk was online, but it's actually offline. It's this John.
But it is the order that's on the website.
Yeah, should
Okay.
be good.
Great.
It's just the third one. We have a video.
And all the slides are now on the thing. So.
No, I would hope so, but I think we have 4 or 5, so that's why probably like
Okay, maybe we can start another 2. Or I think they're
Yeah.
maybe wait one. Yeah, just.
I'm just maybe
Well,
Excuse me, for this afternoon speakers, could you please quickly send your presentation to this email? Thank you.
Non mais tu gères, c'est une folie. T'es en train de.
Il faut.
Non, vraiment, tu gères. Tu régales. Mais parce qu'il y en a qui doivent l'avoir sur leur ordi parce que c'est pas le bon format, c'est ça?
Ouais, c'est ça. Il y en a un, c'est
And you guys will take care of putting up the slides? Or?
Yeah, no problem.
Okay, so I just have to announce it.
Yeah, exactly.
Okay, just checking.
Yeah, exactly.
Press
Yeah, no,
longer.
just wait a
just
sec,
wait.
and now
It's
should be good.
Yeah, sounds good. Just give me the maybe once it says 1434.
Excuse me, just for, if you cannot send by email, can you just come by quickly for the speakers so I can give you a USB key? Thank you.
When should we start?
Yeah, just a second, just checking this one and then.
Okay, we will get started with one of the penultimate sessions of the day. So welcome to this session on online algorithms. We'll begin with the first talk on rate-preserving reductions for Blackwell approachability by Christoph. Did I get that right?
All right, great, yeah. Hi, everyone, I'm John. I'm going to talk a little bit about some stuff we've been doing with Blackwell approachability. This is all joint work with a bunch of other great researchers at Google Research. So at a very high level, this is a talk about two problems in online learning. The first is a problem I expect a lot of you are probably familiar with. It's the problem of just external regret minimization, like just online decision-making over multiple rounds, where at the end of the day, you want to have low regret with respect to the best fixed action in hindsight. The second problem is Blackwell approachability. Maybe you know what this is, maybe you don't. I'll explain in a few slides. But for now, all you need to know is that it's a pretty vast generalization of external regret minimization, and it captures a whole host of other problems in online learning. Like it captures swap regret minimization, it captures a lot of variance of calibration, multi-objective optimization, and so on. So Blackwell approachability is much, much more general than external regret minimization, but nevertheless, there's this seminal result by Abernethy et al. In 2011 that showed that in some sense, these two problems are equivalent. Specifically in the sense that if I give you an instance of Blackwell approachability, you can reduce it to another instance of online linear optimization, such that if you can solve this instance of online linear optimization with regret RFT, this translates into a bound on how well you could solve the original approachability problem. So this is great, and I think ever since then there's sort of been like a tacit understanding that like Blackwell approachability is in some sense equivalent to external regret minimization. If you're like faced with a problem and you can write it as an approachability problem, you should just solve the underlying online linear optimization problem. But there's like one thing which this reduction sort of hides, which is whether this reduction is quantitatively tight. So specifically, like I said, it works in one direction. You know, if I take this Blackwell approachability problem and turn it into an online linear optimization problem, any rate you can get for this regret minimization problem translates to a rate for the Blackwell approachability problem. But can you get the best rates for the Blackwell approachability problem by doing this? Like, does it suffice to just look at this downstream online linear optimization problem? And perhaps like the main contribution we do in this is we showed that the answer is no. There are approachability instances which are trivially approachable, like you should think this is like zero regret even, but where the regret minimization instance you get by going through this reduction has a non-trivial regret bound. So think of like omega of square root t or something like that. On the more positive side, you can recover something. So you can, we don't know how to show an equivalence with external regret minimization, but we can show that all approachability instances are reducible in a rate-preserving manner to this family of online learning problems that we call improper fee regret minimization problems. And I'll explain what those are in a little bit. So just put things a little bit more on a formal footing. So first of all, what's online linear optimization? Again, probably you guys are somewhat familiar with this, but just to introduce some notation. It's a repeated game between a learner and adversary. Every round the learner picks an action from a convex action set P, and the adversary picks a loss from a convex loss set L. It's just linear, so the learner suffers this like inner product loss between their action and the adversary's action, and they want to minimize regret. And we understand this problem pretty well. You know, FTRL will give you sublinear regret. We even know like the tight bounds in a lot of cases. So now let's talk about what Blackwell approachability is. So Blackwell approachability on the surface looks similar, but it's a generalization. So just like before we had an action set and loss set, we still have an action set for the learner and a loss set for the adversary, but now we also have a constraint set. And this constraint set is going to be a convex set of bilinear scalar-valued functions from actions cross losses to the reals. And as before, it's a repeated game where every round the learner picks an action, the adversary chooses a loss vector, but instead of just trying to minimize like the external regret objective I mentioned earlier, now we want to minimize the approachability loss, which you should think of as maybe as the maximum constraint violation of any constraint in your constraint set. So formally, it's the maximum over all u in this constraint set of the sum of u of pt comma lt. And there is not all constraint sets are solvable in the sense that you can get sublinear rates, but Blackwell's original theorem gives a characterization of when you can get sublinear rates for this problem, and it's exactly when the instance is constraint satisfiable. And basically this just means that for all the constraints in your constraint set, there has to be like a best response action you can play that guarantees that you satisfy the constraint, that guarantees that u of p sub u comma l is less than or equal to 0. One quick note, you might have seen many different definitions of Blackwell approachability before in terms of like, vector valued payoffs approaching a set. This is entirely equivalent, and I think maybe a slightly cleaner way to think about this. Okay, so quickly let's put this on some more concrete footing. Approachability can capture standard regret minimization. One way to do this is you should just set your constraint set to be the set of all bilinear functions of the form u of p comma l equals the inner product of p and l minus the inner product of some fixed benchmark action p star comma l. Basically, this is the external regret with respect to the fixed action p star. And just from the definition of approachability loss I mentioned, the approachability loss in this example, it's like the maximum external regret with respect to p star over all p stars. This is exactly the external regret. And you can check that it's constraint satisfiable, and this type of construction also generalizes pretty easily to capture other types of regret you might have seen, like swap regret. Okay, so I said that there's this reduction by Abernethy et al. That reduces this approachability problem to an online linear optimization problem. How does it work? So it's very simple. It's entirely on this slide, basically. So the idea is that instead of trying to produce an algorithm that plays actions over time, we're going to produce an algorithm that produces constraints over time. So it's going to produce u sub t's. And then we still have to play an action. What action will play is we're just going to play the action that's guaranteed to exist by constraint satisfiability. So we're going to play the action p sub t that guarantees that u sub t of p sub t comma l is in most 0 for all l in our loss set. All right? And then you can take this form of approachability, which is the max over all u's. You can add in this extra term, which is guaranteed to be in most 0 because of the constraint satisfiability. And then you end up with an external regret. So this max over, you have a quantity which is maximized over this constraint set u minus the sum of these UTs you actually played. And so if you have an online linear optimization problem with online linear optimization algorithm that works with action set u and reward set like p cross l that gives you like an reward u of p comma l when you see p comma l, you have an algorithm for Blackwell approachability. This is the reduction. Why isn't this reduction type? So there's maybe two reasons you can point to. The first is that, like, we added in this like slack that's less than or equal to 0, and it might be like strictly less than 0, so maybe there's some slack there. Turns out this is actually not a big source of the issue. The much more important source is that the reduced OLO problem pretends that these P sub t's are completely adversarial. We pretend that this like P sub t comma L sub t pairs are generated by an adversary when we like design our OLO algorithm. But in reality, we choose P sub t. We sort of like, chose it originally to satisfy some constraints, satisfiability constraints, but we have a lot of flexibility to choose it. So just by using this observation, it's actually fairly easy to come up with what I said earlier, an instance which is trivially approachable, but where the reduced regret minimization instance has a non-trivial regret bound. And the idea, in like one line, is just to take a non-trivial approachability instance and add a dummy action which guarantees approachability. And then when you run it through this reduction to OLO, you end up with some online linear optimization problem which doesn't know that you can just play this like P star, so it has to be adversarially robust against any adversarial sequence of P sub t's and L sub t's, and this is too much to hope for. So this is one thing we do. The other thing we do, or one of several other things we do, is we show that you can reduce it to this problem called fee regret minimization. So fee regret minimization is a generalization of swap regret, if you've heard of that, introduced by Gordon et al. The idea is that it's a regret minimization problem, just like external regret, but instead of comparing to the best fixed action in hindsight, you compete with the best fixed transformation in hindsight, where the transformation is drawn from some set of transformations. So you can think of this sort of like the context, the constraint set before. So it's specified by this action set, this law set, and this transformation set that contains linear functions mapping the action set to itself. Again, you choose actions, adversary chooses losses, and you want to minimize this fee regret, which is the regret compared to the best fixed transformation in hindsight. Okay. Why is there the word improper in this improper fee regret? So traditionally, in this Gordon et al. Introduction of fee regret, they considered maps of linear functions that mapped the action set onto itself, which makes sense. You want to compete with like viable, proper actions. But actually, it turns out if you look at like what's possible via approachability or the original reduction, it suffices that your transformation set just has the property that every transformation in the set contains a fixed point in the original, this should say a fixed point in P. So every transformation needs to have a fixed point in P, but it can map actions in the action set to actions that you can't play. And these transformation sets are still possible to get sublinear regret with respect to, and they are a strict superset of proper fee transformations because of Brouwer's fixed point theorem. So we show that you can get two-way reductions between the class of Blackwell approachability instances and these improper fee regret instances. There's a lot of stuff we do in the rest of the paper showing that reducing to improper fee regret as opposed to proper fee regret or external regret is somehow necessary. We sort of like characterize which problems are equivalent to which under like changes of variables, linear transformations. There's a lot of nice math there. But in the interest of time, that's all I'm going to talk about here. Thanks for listening, and happy to take any questions.
Thank you. Questions?
So I was hoping you could say a little bit more about how easy is it to solve these like fee regret optimization problems versus like online linear optimization.
Great question. So we showed that it suffices to solve these fee regret minimization questions. In some sense, the best like general class of algorithms I know to solve them is this reduction to online linear optimization. But recently there have been some cool algorithms which sort of don't fit in this framework that you can also use. Like, so there's these like tree swap algorithms which really only make sense when the dimension is very, very large. So it's sort of outside the scope of like the specific things we were considering here. But you can use those algorithms to solve any proper fee regret minimization problem. And as far as I know, there's no way to really think of it as like going through this reduction. But yeah, I think it's a big open question, how to design algorithms for these problems.
Okay.
Sorry.
Sorry. One question here. What does the class fee look like when you go through this reduction?
What is the class? Yeah, so I didn't explain how to prove this at all, but it's something you basically get by staring at one of these definitions of approachability. So it's equal to like a max over. Maybe ask me offline. But like basically, you stare at this and you try to rewrite it as a fee regret, and like it's very like similar to the set of views. It's in some sense like isomorphic.
I guess one last question. So in the improper in the improper definition, why do you need phi to have a fixed point in P? Is there any?
I mean, one like clear counterexample is if I had like a constant map phi, which just like mapped like all the points of my action set to some point outside the action set.
Yeah.
You can imagine online learning problems where you're going to like necessarily incur linear regret, right? Because that point's just better than anything inside your action set. But it turns out just having a fixed point
suffices.
Yeah.
Very interesting. Thank you.
Okay, I had a question, but I'll ask it offline in the interest of time. Thanks again. The next talk is on optimal online bookmaking for any number of outcomes.
Okay, hello everyone. I'm Adar, I'm a master's student at the Hebrew University, and I'm really excited to present our paper, which is joint work with my advisor, Dr. Oron Sabag. This talk is about bookmaking, the problem of assigning odds to uncertain events. And don't worry, it's all theoretical, no bets were placed in the making of this talk. So what's gambling really about? An event has k possible outcomes. For example, a tennis match has 2 outcomes, soccer has 3, win, lose, or draw, and Eurovision 2025 has had 37 countries competing. And the bookmaker proposes the following. It publishes odds gamma k for each possible outcome k, and one can place a bet of assume $1 on any outcome k. If k is the event's outcome, you receive gamma k dollars, and otherwise the bet is lost. Let's look at a concrete example of a betting on a soccer match. Here the event is El Clasico, so there are 3 possible outcomes, and each outcome has a corresponding payoff gamma k. For example, if you bet on Barcelona and they win, you get 2.4 times your money. The implied probability of each outcome k is given by 1 over gamma k. And to obtain a proper probability vector, we normalize each implied probability by the sum of all implied probabilities. This sum, denoted by capital gamma, is the overround. It measures how much the total implied probability exceeds 1, and the higher the overround, the less fair the odds. For example, in this example, here the overround is 1.25, and usually for 3 outcomes, the overround is about 1.15, and for 24 outcomes, for example, in UK football, it raises up to 1.6. So they really need this margin. We denote the normalized probability vector by R. We've seen our bookmaker set static odds for an event, and online bookmaking repeats this over time with dynamic odds that respond to bets. An online bookmaking game consists of T, which is the number of betting rounds, K, the number of possible outcomes for a single event, and gamma, which is the overround. Note that the bookmaker chooses both the number of rounds T and the overround gamma. For example, they can open betting a week before the event and update the odds every minute until it starts. At each round T, The bookmaker selects odds vector RT in the k-dimensional simplex, and the gambler distributes a betting unit according to some distribution QT, where the kth coordinate of QT is the portion of bet placed on the outcome K. After T rounds are played, the true outcome K is revealed. Then the gambler's total return is the sum over all rounds of their bet on the realized outcome K, scaled by the payoff. We consider the bookmaker's worst case scenario, where the event's outcome results in the largest return, and the gambler maximizes the bookmaker's loss. The optimal loss, denoted L star TK, is defined by this game, where the bookmaker minimizes over their sequence of odds. Note that the overround is omitted from the optimal loss. However, the optimal loss directly characterizes the fundamental limits of the overround. The overround should be at least 1, as the optimal loss is greater than or equal to T. This follows from comparing to an easier setting where the bookmaker reacts after seeing the gambler's bets. When gamma equals 1, the bookmaker odds are considered fair. In this case, the odds match the implied probability. Finding the optimal loss is difficult. At each round, the bookmaker sets the odds based on everything that happened so far, the previous odds and the gambler's past bets. And moreover, it's actually a vector-valued game. We need to control a whole vector, one entry for each possible outcome. So, as Christopher said, Blackwell introduced a generalization of repeated games to vector-valued payoffs. And however, our objective function behaves like 1 over R. And for similar reasons, online learning algorithms that assume bounded or Lifshitz loss functions won't apply here. In particular, the odds may approach the simplex boundary. Even if we could use these methods, constant factors matter in our betting setup. And note that the exponential growth of the game tree makes backward induction computationally infeasible. Our first result characterizes the optimal bookmaking loss. For any number of rounds T and any number of outcomes K, it is exactly equal to a certain polynomial, built using binomial coefficients and the rising factorial. Importantly, this polynomial is easy to compute, and its degree is only K, so the computational complexity does not grow with T. We illustrate the loss with special cases. For K equal to, L is T plus square root of T, and this reveals the optimal loss for binary games. For K equal to 3, the optimal loss takes the following form, and we see that the coefficient of square root T converges to square root 3 as K goes to infinity. We can write the optimal bookmaking loss as following. The second summand is the regret. It is measured with respect to a bookmaker that foresees the aggregated loss, but does not know the aggregated bets and does not know the event's outcome. Note that if beta converges as T goes to infinity, then the bookmaker can reach fair odds. Our next result establishes that convergence. As the number of rounds T goes to infinity, beta converges to the largest root of the well-known K-thermite polynomial. And this really shocked me. I was like at 3 a.m. writing some equations and then got to know that there's a Wikipedia page after what I found. Consequently, by Krasikov, beta k equals to square root of k, and plus a little o of square root of k. And know that for any fixed t, beta tk diverges as k goes to infinity. We then ask the fundamental question in game theory: what happens when the environment is not as adversarial as expected? It means that we don't actually meet an optimal adversary. We model this as follows. The bookmaker receives a state S, reflecting committed payouts, and should design a strategy for each remaining rounds. We establish a Nash equilibrium for the game. If the gambler bets decisively in each of the remaining rounds, the bookmaker is forced to return the optimal loss. And the optimal bookmaker conversely guarantees the same loss for any decisive gambler's betting sequence. As you can see on the left, this is a decisive gambler where all the bet is on one outcome. If the gambler is not decisive, then we can leverage this opportunity to reduce the loss. Formally, the optimal opportunistic bookmaking loss is the following. It quantifies the total payout for outcome K, combining the prior commitments encoded in SK and the additional payout incurred over the remaining age rounds. We characterizes the optimal opportunistic loss as the largest root of a certain polynomial f. It generalizes the optimal loss and allows finding the optimal loss for any given state. It's a sum of terms involving powers of x, where each coefficient is built using a combination of following factorials, binomial coefficients, and the elementary symmetric polynomials of the state vector. This polynomial can be computed in order k square time, and its complexity and degree remains independent of t. Moreover, we established the optimal bookmaking strategy using the residual loss vector. As shown in the figure, it's the gap between the uniform optimal loss and the current state. We provide an explicit formula for the optimal odds as a ratio of two polynomials constructed from the residual loss vector. We present an efficient forward algorithm that computes the opportunistically optimal bookmaking strategy. At each timestamp, we update the state vector based on the last betting round. If the gambler was not decisive, we reduce the loss, and then we calculate the residual loss vector and use it to output the optimal odds. The algorithm is forward running with pair round complexity of order k squared. So to conclude, bookmakers can achieve the lower bound gamma greater than 1 for large T. We provided explicit solutions and a simple, in my opinion, efficient algorithm. We extended our view to the opportunistic strategies in repeated games, and future work might consider geometric analysis of the optimal algorithm or other objective functions beyond online bookmaking. Here's the paper if you are interested, and thank you so much for listening.
Thank you. Questions? I had a quick question. You mentioned a solution in terms of roots of Hermite polynomials, so I'm curious if you could say more about where the Hermite comes from. I didn't see any Gaussians anywhere in your talk.
So actually the whole analysis, as you can also see in the optimal loss, it was combinatorial. Like the way to solve it was to actually, we called it the Bellman Pareto. We were able to characterize as what the vector V, the residual loss vector, should be, like what should be its structure. And actually, it was not trivial for me to find out what happens when it goes to infinity. Like we had to transform the following factorials into generating function of and involving Stirling numbers and that stuff. And by other smarter mathematicians than me, I saw that like it's actually the Hermite polynomial. So it's saying that like there's something really foundational in the uncertainty regarding this stuff because it's mostly like in quantum stuff and think I don't understand it.
Yeah, very, very interesting. Thank you.
Thank you.
Okay, let's thank the speaker again. The next talk will be a virtual talk. Oh, they're online on Zoom? Okay, I'll announce the talk.
This is Akash, and I will be talking about our paper, A Gap Between the Gaussian RKHS and Neural Networks, an Inference Center Asymptotic Analysis. This is a joint work with Rahul Parhi and Mikhail Misha-Belkin from UCSD. So far, neural networks have taken the world by storm. They are the state-of-the-art model for most
Akash,
tasks.
there's an issue. Oh, no, I
They
think
seem
it's
to
resolved.
overcome the curse of dimensionality by learning low-dimensional representations. And in bounded domain, they are also known to be universal approximators. But they do come at the cost of being opaque. So in this work, we ask a very simple question. To what extent can neural networks approximate any class of functions? So far we know that even at depth, two neural networks can approximate any continuous function in a bounded domain under Fresnel activation functions. But what can we say when the space is unbounded or target function is discontinuous? To this, we have an answer for the unbounded case, where we saw that shallow networks can't approximate some functions from Gaussian RKHS. And we first define these quantities, and then we'll show the final result. So first, a shallow ReLU network is a single hidden layer network with input weight Wk, output weight Vk, corresponding to a ReLU activation function, where for width k, ReLU network has this functional form, and the infinite limit it has an explicit form of, in the form of an integral where we take a measure on unity sphere. So recent work has studied the representational cost of writing a function and an infinite width two-layer ReLU network. Where in the finite case, we simply compute the Frobenius norm of the input weight and L2 norm of the output weight. And the infinite width limit is defined by taking the limit over epsilon turned into 0 for approximations for the target function f. For odd dimension d, this computation can be simplified, and this coincides with a norm that has been studied a lot lately called second order Rodon total variation norm, which is computed by taking this measure after computing the RAM filter of the Rodon transform. This can be simplified in the odd dimension d, and by simply taking the d plus 1th derivative of the Rodon transform. For this work, we need some of these definitions that I'll go over now. So a Rodon transform is computed by taking an integral for each normal direction gamma with respect to or d minus 1 dimensional vague measure on the hyperplane. A Rodon bounded variation space is defined corresponding to a bounded RTV2 norm within the space of L-1 functions, which are basically a Banach space of functions with at most linear growth. Now, this RBV2 space is interesting because they capture shallow ReLU networks, and they have been studied a lot lately. And Rahul and Parhi showed that if we define an optimization on the space of RBV2, then it admits an optimal solution in the form of a two-layer ReLU network. Now I will define Gaussian reproduction Gunnar-Hilbert spaces corresponding to a Gaussian kernel that has this form, where the associated RKHS is defined by taking the closure over all functions f that has this linear form corresponding to centered Gaussian kernels. Now, RBV2 is a rich class of functions, and they contain several function spaces such as spectral baron spaces, L2 sublobe spaces. In the bounded domain, one can compare Gaussian RKHS as a tiny subset of RBV2, but the story changes significantly in the unbounded case, where one can show that there exist kernel machines within Gaussian RKHS that don't lie within RBV2 space. Now, how do we show this construction? So this requires three-step process where we first consider a Gaussian kernel machine. Then we compute an explicit form of RTV2 for the kernel machine, which has this complicated double integral form. And now once we have this form, we show a sequence of Gaussian kernel machines corresponding to an infinite sequence of centers that has diverging RTV2 norm. And this was the claim of the work. Now, RTV2 of a Gaussian kernel machine can be computed via this three-step recipe, which involves computing Fourier transform on the kernel machine, which has this form. Once we have the Fourier transform, one can take the one-dimensional Rodin slice. Now, with the Rodin slice, the final RTV2 is computed by taking the L1 norm of the d plus 1 derivative of the Rodin slice, and that gives the final form of RTV2 of the Gaussian kernel machine. But we know that the final form can be simplified by observing this Gaussian derivative, which can be rewritten via probabilist Hermite polynomial. So by a simple change of variable, one can rewrite the RTV2 form in this simplified form, which has an inner integral I inner in terms of Hermite polynomials centered at delta i's corresponding to projections for the centers xi's. Now, if you look at the simplified form, this both informs and suggests that if we pick alpha i's carefully and delta is far apart, then the inner integral can be made to diverge as the number of centers increase. But we need to make sure that one really holds within a cone K so that the RTV2 can be made to diverge. To this end, we can achieve this by simply picking combination alpha that has unbounded L1 norm and centers xi that are well separated within the cone. Now, we are able to show that there exists a cone K so that for each direction beta prime in that cone, the inner integral is lower bounded by the first K linear combinations. And we are able to achieve this goal by simply showing some properties of Hermite polynomials. With these properties, we perform some key steps where we show that the delta is projections are separated by a lower bounded constant delta. Now, for these delta is, we define intervals ni's so that the mean mass per center within the neighborhood contributes at least a factor of alpha I rho, where rho is a constant. And with this, we are able to show that the inner integral is lower bounded. And this gives us a divergence sequence of kernel machines with the unbounded RTV2 norm. And with this, I conclude our work. And so in this work, we have shown that in unbounded domain, there is an interesting story. And there exist Gaussian kernel machines that cannot be represented within RBV2, that is shallow neural networks. There's an interesting future direction to investigate what this gap really entails in a learning setting, to which one can study the rate of convergence of shallow networks for the constructed infinite center kernel machine as a target function. Furthermore, it would be interesting to show a similar gap between kernel methods and deep neural networks that will really capture the approximation gap of these networks. And I finished my talk. I hope you've enjoyed the presentation. Hello.
Okay, so that was a recorded talk, so we'll skip the questions.
Hello, everyone. My name is Alexander Rubchenko, and today I'll talk about online learning with delays, to which we introduce a novel capacity constraint. This is joint work with Idan Atias and Dan Roy. It is natural to extend the classical multi-armed bandit problem to account for delayed feedback. For example, imagine that you have to select one of several treatment strategies for a stream of patients, one patient at a time. Treatment effects take some time to materialize, so realistically, you will have to make treatment decisions without observing feedback from some of the previous patients. However, in the real world, it is also true that this sort of medical feedback needs to be processed by highly qualified physicians, which are in high demand. Therefore, it is natural to ask, what if we have a limited number of physicians that can process concurrent feedback from patient cases? That is equivalently, what if we can track only a few rounds for delayed feedback at any given time? Clearly, we won't be able to observe every delayed feedback. Hence, we want to know what's the optimal way to assign physicians to patients and how many physicians do we actually need to perform well. And the surprising result of our paper is that it's not too many. Formally, the oblivious multi-armed bandit problem with delays is defined as follows. At the start of the game, adversary picks losses and delays for the whole game. Then in each round, a learner takes an action, incurs corresponding loss for that action that is not necessarily observed at this round. To be precise, it is observed at around t plus this round's delay dt. And in this round, the learner observes all delayed losses that arrive this round. As a measure of algorithm's performance, we use expected regret, that is expected cumulative loss of this algorithm in excess of the cumulative loss of a best single action in hindsight. Now we introduce the capacity constraint variant of this problem. Here we have a new parameter, capacity C. The learner will maintain a tracking set of round indices of maximum size C throughout the game, as before adversary picks losses and delays for the whole game at the start of the game. And then in each round, learner takes an action, incurs corresponding loss. Now the learner has to make a scheduling decision whether to start tracking the current round by adding it to the tracking set, provided the tracking set is not full at this point. And the learner observes all delayed losses that arrive this round for rounds that are currently in the tracking set. As is common in online scheduling literature, we propose two optional modifications for this setup. Firstly, we say that this framework is clairvoyant if delay is announced at the start of the round, and we say the framework is preemptive if the learner has an option to remove elements from the tracking set. Otherwise, it's non-clairvoyant or non-preemptive, respectively. In our paper, we study variants of this problem for both full information and bandit feedback. In this presentation, we focus solely on bandits. And the main question we aim to answer is what capacity is sufficient and necessary to match the known bounds for the delayed setting without any constraints. And we are able to show that either under clairvoyance or preemptibility, this capacity can be fairly small. Our general approach to this problem is to separate the scheduling policy from the learning algorithm. Scheduling policy manages how the tracking set is maintained. Specifically, it decides each round whether to add the current round to the tracking set. It provides arriving losses to the learning algorithm, and if preemption is allowed, it can remove rounds from the tracking set. We want our scheduler to act autonomously, not relying on actions taken by the learning algorithm, and this allows us to focus mainly on designing schedulers and we can use known learning algorithms. Like in our paper, we take modified delayed follow the regularized leader algorithm from Zimmert and Seldin, but other delayed algorithms can be applicable here as well. Yeah. Now we move on to results. First, we consider the setting where all delays are equal. In the unconstrained setting, the minimax regret is known to be the following. Square root tk is the banded component, square root td log k is the delayed component. Trivially, if capacity is at least d plus 1, we can observe all feedback, but we'll show that we can do a lot better. Specifically, we prove that the optimal regret is the following. Here, the red factor highlights the contribution of the capacity constraint, and from this regret bound, it immediately follows that optimal capacity, the capacity that is both sufficient and necessary to match the unconstrained regret bound, is the following. It's minimum k over log k and delay d. As number of actions k can be much less than delay d, this is a curious result. Okay. Yeah, so to achieve this bound, we use a batching technique. We partition rounds into contiguous batches of size b. B is parameter of this algorithm. We fix an action to be played within each batch and sample a representative round to act as an unbiased estimator for the whole batch. Then, provided batch size is large enough, the capacity constraint is maintained. Specifically, when batch size is at least approximately d over c, the capacity constraint is maintained. Yeah, the main proof idea is to think of each batch as a round. Then we reduce the original problem to the delayed problem with t over b rounds. We get the following regret, and if we were to substitute the appropriate batch size, we get the claimed regret bound. Now we consider more general round-dependent delays in the clairvoyant and non-preemptive feedback. Here we observe delays, but we cannot preempt. Thus, for each round, we can either commit to tracking it till observation or skip it. Like the known bound for the unconstrained setting is the following. Here, capital D is the total delay. We are able to show the following upper bound on regret. The red term is very similar to the one we had in the fixed delay setting with an addition of a log t factor. Well, capital D over capital T is average delay. Importantly, this bound only holds when capacity is at least of the order log t. And it follows that optimal capacity is then basically the one from fixed delays multiplied by log t. This is an upper bound. Yeah, the question of whether we can remove log t term here is an open question. We suspect that it's impossible. Yeah, algorithmic idea here is Bernoulli scheduler. We have a sequence of probabilities, of round-dependent probabilities pt, and each round we schedule this round with probability pt, provided the ring set is not full. We choose pt approximately of the size c over this round's delay and log t factor. Motivation for this comes from the fixed delay case where optimal sampling rate was about c over d, and thus we get sort of adaptive batching with various delays. Yeah. Okay. And then by choosing appropriate learning rates, we get the claimed regret bound. In the non-clairvoyant and preemptive setting, yeah, we have the same baseline, and we're able to show the following regret with a new term that depends on dmax. Dmax is maximum delay. Yeah, removing dmax is an open question. Our approach here is to sample proxy delays. Proxy delay, like from some round-dependent distribution, and then we commit to tracking this round up to time t plus this proxy delay. Hence, observation occurs if and only if proxy delay is at least as large as delay. It turns out that choosing Pareto distribution with shape parameter equal to 1 and scale parameter equal to C over log T is like gets us like the claimed bound. All in all, multi-arm bandits with delays have been extensively studied. Our capacity constraint introduces a new direction that will be interesting to study, for example, for contextual bandits or delayed settings with arm-dependent delays, and there are still bounds, some gaps in our bounds. Thank you very much.
Thank you. Any questions? Okay, if not, let's thank the speaker again. The last talk of the session will be by Vasilis Tsirkanis on structure-agnostic optimality of doubly robust learning for treatment effect estimation.
So first of all, this is joint work with my amazing student Jikai Jin, who could not attend and present this work. So you're stuck with me, presenting what is truly Jikai's work. So obviously from the title, this is not an online algorithms paper, but due to scheduling constraints, the program chairs accommodated, and I'm presenting in today's session. So first, let me start by doing some basics in causal inference, which is the basic premise of this work. So we're going to be interested in understanding the statistical limits of estimating average treatment effects. So first, let me define what an average treatment effect is. The basic framework for causal inference is the potential outcomes framework, where we assume that nature generates two potential outcomes, y1 and y0, where y of d is the outcome we would observe if a unit had received treatment D in 0 or 1. And in the data, each unit receives some treatment capital D, and we observe the potential outcome for the assigned treatment. What we want to estimate is the average treatment effect, which is the average difference between these two potential outcomes in the population. And obviously, for each unit, we only observe one of the two potential outcomes. However, if we assume that we observe enough variables x, typically called controls, such that once we condition on x, the assignment of the treatment is as if it was coming from a randomized trial. Formally, this is defined by saying that the potential outcome random variables are independent of the treatment assignment conditional on the controls. Then this average treatment effect can be identified from the data via what's known as the G formula, which basically says fit a bigger predictive model that tries to predict the outcome from the treatment and the controls, and then average the predictions of that model when you flip the treatment variable on and off, and you average over the controls x. So now, this is the quantity we're trying to estimate. So we assume that we have n IID samples, where each sample contains controls, treatment, and outcome. And our goal is to estimate the parameter θ0, which is the average difference between two predictive models. One predictive model that predicts the outcome using the controls x among the treated population, and another predictive model that predicts the outcome from x in the control population. And what this paper is about is what is the optimal rate achievable for that parameter θ0, which is the average treatment effect. First, what are good algorithms or good candidate upper bounds for that statistical limit? One such very celebrated algorithm is the doubly robust estimator, dating back to the seminal work of Robbins in '94, where the idea is that, well, this original formula that I presented in the previous slide for the average treatment effect is a bit sensitive to errors in those predictive models G, these outcome predictions. And so the idea is that we want to add a correction term to that formula that corrects error in estimates of those outcome predictors. And so how does that correction look like? Well, those outcome predictors are supposed to be predicting the outcome y, and so we can use the residual of that prediction as a signal of regions where that predictive model is making mistakes. So if that residual is not close to mean 0, conditional on x, then that's a signal that the regression model for the outcome is wrong. And so we should add that signal into the formula to counteract errors in G. And the way that we add it is we need to multiply that error in prediction by a function that will translate errors in prediction into errors in the average treatment effect. And a function that works here is what's known as the signed inverse propensity. And so that's the function that you need to plug in there, and that's how you derive the doubly robust estimator. And in particular, we're going to look at the sample splitting variant of the doubly robust estimator, where you split your samples in half. In the first half, you estimate these outcome regressions and the propensity, and in the second half, you plug in those predictions of those estimated models into the doubly robust formula, and you average over the second half of the data. And you can show that in finite samples, this doubly robust estimator is going to achieve an error that depends on the product of the mean squared error of the outcome regressions and the mean squared error of the propensity. So the squared difference in the average treatment effect will be upper bounded by the product of these two mean squared errors plus a parametric term of 1/n that cannot be avoided. So the question now becomes, is this optimal, and can we do better than this doubly robust estimator? So the answer is sometimes yes. So there is actually a line of work that shows that if you know more information about the function spaces in which those true regressions and propensities lie in, and that space is well behaved, for instance, some type of kernel Hilbert space, then you can further correct for mistakes in those estimates G hat and P hat and beat the estimation error of the doubly robust estimator. However, the estimation algorithms that you typically get with these approaches that try to do these second-order corrections are quite brittle and impractical. In particular, these extra corrections that you're making are very much tailored to the function space. And the resulting estimation algorithms that you get are less practical in that many times they require that you know ahead of time some growing sieve basis that is well aligned with the top eigenfunctions of the space in which your regressions lie in. And so these are quite brittle assumptions. And moreover, these estimators do not really reduce the estimation of the average treatment effect to general purpose machine learning-based regression models. And so we're going to sidestep these improved results by saying, what if all we're willing to assume is access to good regression oracles and no other structural assumptions on the data generating process? This is the structure-agnostic optimality framework that was recently introduced by Balakrishnan et al., which basically says, suppose that someone just gave you access to regression estimates for the propensity and the two outcome regression models, and told you that those regression estimates achieve some mean squared error of epsilon p, epsilon g, etc. And that's all you know about the data generating process. So then what is the best achievable rate when the data generating process can follow any law that is consistent with these mean squared error bounds? The prior work of Balakrishnan et al. That introduced this framework provided such statistical limits within the structure-agnostic framework for several parameters of interest, which, however, did not include the central causal quantity, the average treatment effect. And so this was an obvious gap in the literature before this work. To introduce our main result, first let me do some simplifications and some regularity assumptions. So the first simplification is we're going to focus on the case where the outcome is binary and the covariates are uniformly distributed in the hypercube. A lower bound for this, under this simplification, can only be a stronger lower bound. And so this is more like a benign simplification. The nice thing that this tells us is that now the data generating process, the law of the data, can be fully determined by the propensity and those outcome regressions. So now the density of the data is really just the product of the propensity and the outcome regression. Moreover, we're going to assume that both the propensity and those outcome regressions are bounded away from 0 and 1 by some constant c that's strictly positive. So let me now introduce more formally the structure-agnostic minimax lower bound. So we assume that we have access to regression oracles that are assumed to have some mean-squared error rates that can also depend on the sample size. And we consider all possible distributions F that are compatible with the mean-squared error bounds. So we consider all such densities F that are some product of some P and some GD, such that the P and GD are within those mean-squared error balls. And then the structure-agnostic minimax lower bound is basically, it is T and gamma if for any estimator there exists a feasible distribution such that with probability at least gamma, when seeing samples from that distribution, the squared error of the estimator is at least T and gamma. And our main theorem is that for any gamma, the structure-agnostic minimax lower bound for the average treatment effect is exactly, up to constants, the error rate that is achieved by the doubly robust estimator. Some proof insight. The proof is enabled by a novel family of local random perturbations for the method of fuzzy hypothesis that was also used in prior works, but we had to develop a new family of perturbations. And notably, I want to make a point that minimax optimality for the average treatment effect, even in classical minimax optimality frameworks, is only partially addressed. We don't really know of a complete characterization, even in classical minimax optimality frameworks, which showcases how distinctively hard the average treatment effect is as a statistical object. And so this gives some more sort of like, says why this result is also non-trivial, even if you view it beyond the structure-agnostic minimax optimality framework. To give you a very broad picture of the proof, the method of fuzzy hypothesis says you have, say, your estimator that's consistent with these estimates f hat. You try to construct a family of other candidate densities that are also feasible, such that when you sample data from f hat, you get some data sets. When you sample data by first drawing a distribution from the family and then drawing data from that distribution, you get a very similar looking data set with respect to the Hellinger distance. But when you project f hat to the parameter space, and when you project that family to the parameter space, you have a separation of at least S. So you try to construct such a family. How we're going to construct such a family? Suppose that this is, visually the original density. We're going to construct local deviations that basically look like partition the space and flip a step function plus or minus, and then add that locally randomly flipped sign step function to the density with some weights. And this will be the elements of that family for a random choice of those flips. And then we need to construct a way to add those perturbations based on some complicated scalings that are non-uniform and coupled across the different parts of the density, such that we can satisfy some important properties that would lead to both a Hellinger distance bound and the separation bound. So the construction of these perturbations is the crux of the proof, and moreover, we need to take different case analyses dependent on which of these estimators has smaller or larger error rate. In the paper, we derive also results for several other key causal quantities, such as a weighted average treatment effect and the average treatment effect on the treated. So the take-home message is that the doubly robust estimator is structure-agnostic minimax optimal for many central causal parameters of interest. Thank you.
Thank you. Do we have any questions?
Just a quick question. Can you give some intuition for how you get the product of the two epsilons in the lower bound?
So if you look over here, let me give you over here. Okay. So this is our second perturbation, which because of this ratio is basically g hat plus epsilon 2 and 1 minus epsilon 1. Okay, so you have this coupled perturbation both in the numerator and in the denominator.
Got it.
And you can go down here, it says this is approximately this plus that, and you get a second order term, which is delta square, and delta square is always 1. And epsilon 1 is supposed to be of the order of the propensity deviation, epsilon 2 of the order of the regression deviation.
Great, great.
Okay.
Yeah, so when you construct your distributions, you're doing these small local perturbations, which sort of makes it feel like it would have a very large fat shattering dimension, for instance. So if we are willing to place that another restriction on a class is that the fat shattering is sort of small, which is usually nice to get nice rates. Do you think this sort of lower bound will still hold? Because I don't think even if you assume fat shattering, doubly robust estimators get better rates.
If you assume such classes of the form that you say that are beyond smoothness, maybe this will still hold. The crucial thing here that maybe that is the bottleneck is that the partitions that I'm creating have to be basically of the same order as the sample size. So each step function is in a 1 over n range. So maybe I don't know what the fat setting of that would be.
Thank you.
Okay.
Let's thank the speaker again. Before everybody leaves for the break, the local chairs wanted me to mention that the virtual speaker, I think Akash Kumar, is available for questions if anybody had any about his talk. Yeah, or if there are no questions, we can just clap for him, if that works. Okay, thanks to all the speakers for a great session. We'll break. I'll just put this somewhere here.